Alright, today we're going to talk about section 3.4, solving systems of equations in three variables. Well, I call that 3x3 systems. We're going to be solving 3x3 systems. And we're going to be doing it much like we did in 3.2 with the 2x2 systems, but again, things are a little more complicated by the addition of a new variable. Alright, let me give you an example of what a 3x3 looks like. This is example 2 on page 265. Give me a minute here. I want to make sure I copy this correctly. One little mistake can send you reeling in these 3x3 problems. Things get complicated very quickly, as you might imagine. Alright, here's a 3x3 system. I'm going to number these equations 1, 2, and 3. And we are asked to solve this 3x3 system simultaneously. In other words, find an ordered triplet. In other words, x, y, and z values that will solve all three equations all at the same time. Alright, we're going to give you a little bit of a guide here. It's much like the 2x2s. Step 1, we're going to pick any two of these three equations and eliminate a variable, much like the elimination method we used in section 3.2. Step 2 then. Pick a different pair and then, using elimination techniques, eliminate the same variable. Step 3, well, steps 1 and 2 will result in a 2x2 system. So take those two equations and solve the resulting 2x2, which will solve for two of the three variables. And step 4, once you've got two variables solved for, you can easily solve for the third by taking one of the original equations and then solve for the third variable. Let's look at the example given here. And I'm going to pick equation 2 and equation 3. Let me write that down here. If I add equation 2 to equation 3, we can see the z variable gets eliminated quite nicely. Look at 4x minus y equals 10. Already I found a mistake. Please make this correction. It's so important to not make any mistakes. That should be a 1. Copy error as I copied it from the book. Okay? So adding equation 2 to equation 3 gives me 4x. Let me check it. 4x minus y equals 10. Again, please make this correction here. Alright? Alright, I now see I'm going to want to pick a different pair and eliminate the same z variable. If I take equation 3 and multiply it by 2 and add it to equation 1, I'm going to eliminate this same z variable. Let me leave this aside for now. Circle that. If I take equation 1 and add that to 2 times equation 3, I will eliminate that same z variable. Let me show you what I'm talking about here. I'll take equation 1, 2x plus y plus 4z equals 12. And I take 2 times equation 3. Let me do that in my head. 2 times 3x is 6x. 2 times minus 3y is minus 6y. 2 times minus 2z is minus 4z. And 2 times 1 is 2. I think you can see we are going to eliminate that variable, z variable again. Alright, the resulting addition would be 8x minus 5y equals 12 plus 2 is 14. So I get a second equation where z is eliminated. Alright, so I've executed steps 1, 2, and 3. Again, adding equations 2 plus equation 3 gives me this equation. Doing a little surgery, adding equation 1 to 2 times equation 3 gives me this equation, and z is eliminated from both of those. So I can get a resulting 2 by 2. So 4x minus y equals 10, and 8x minus 5y equals 14. Alright, so now I'm going to solve the resulting 2 by 2 equation. Well, I'm going to multiply, let me write this down again here, 4x minus y equals 10. And this is the resulting 2 by 2 equals 14. Alright, now I'm going to solve the resulting 2 by 2, and I'm going to use the elimination method. I'm going to multiply the top equation by minus 5. Why minus 5? Because I see I will then be able to eliminate the y variable when I add the resulting system. Multiplying the top equation through by minus 5 gives me a minus 20x plus 5y, be careful of the signs, equals minus 50. Right? Let me check it. Minus 20x plus 5y equals minus 50. I'm going to leave the second equation alone, and that resulting 2 by 2, because now I see when I add these two equations, I'll eliminate the y variable. I'll get minus 12x equals, the y's cancel, minus 36 on the right, and of course then x equals positive 3. And once I get a solution for a variable, I'll circle it so I don't lose it in the blizzard of writing here. Alright, if x is 3, well, I can go to now either of these equations and solve for y. I'll pick the top one. 4 times 3 minus y equals 10. 12 minus y equals 10. So minus y equals minus 2. And of course y equals positive 2. So I see when x is 3, y has to be 2. And now I'll execute my last step. I've got two variables solved for. I can go up to any of my original equations. I'm going to pick the top one, plug in my x and y values, and solve for the unknown z value. So taking equation number 1, let me write it down again. 2x plus y plus 4z equals 12. So when x is 3, y is 2, and I can use those values of x and y to then solve for z. So 2 times 3 is 6. 6 plus 2 is 8. 8 plus 4z equals 12. 4z equals 4, of course, and z then equals 1. So when x is 3, we know y must be 2, and of course z must be 1 to solve this 3 by 3 system. So I think our author would give our solution in ordered triplet format. And again, instead of xy, we've got xyz. And we usually put the variables in alphabetical order. X is 3, y is 2, z is 1 is my solution for that 3 by 3 system. Alright, so again, much like we've done in section 3.2 with a new wrinkle, and again, good housekeeping is key. This one's from your homework list. This is number 15. I believe it's the first one on your homework list on page 272. Solve the following system. Let's see. X plus y plus z equals 4. 2x plus y minus z equals 1. 2x minus 3y plus z equals 1. All right, this is a 3 by 3 system which we are asked to solve. In other words, find the solution, find the x, y, z triplet that solves all three equations simultaneously. Alright, I'm going to label these equations 1, 2, and 3 and follow our procedure. Now, again, the procedure is, well, to pick two equations, eliminate a variable, pick another pair, eliminate the same variable, take the resulting 2 by 2 and solve as in section 3.2, and then use one of the original equations to solve for the third variable. Alright, I think I see something happening here. I'm going to take equation 2 and add that to equation 3. If I do that, these z variables will cancel out. Right, if I can do this in my head, 2 plus 3, I'll get 4x minus 2y. The z's cancel out, and I get that equals 2. Okay, adding equations 2 and 3. And I see if I add equations 1 and 2, I can also eliminate the z variables, right? They are opposite coefficients of opposite z coefficients in equations 1 and 2. All right, adding equations 1 and 2, I get 3x plus 2y equals 5. All right, so here is my resulting 2 by 2 when I eliminate the z variables. Well, this turned out nice. The y coefficients are opposites, so I can easily eliminate y from the resulting 2 by 2 just by adding the undoctored equations. I'll get 7x plus 0 equals 7, and x, of course, is 1. And again, I like to circle variable values once they're solved for, lest they get lost in the shuffle. Alright, if x is 1, I can pick either of these equations to solve for y. I'll pick the second one. 3 times 1 plus 2 times y must equal 5. So 3 plus 2y equals 5. 5. So 2y equals 2. And of course, y also equals 1. And let me circle that. Alright, so when x is 1, y is 1. Now I'll take that solved 2 by 2. In other words, take these x and y values, go back to any one of these original equations, plug in x and y respectively, and solve for z. And I believe the top equation is the simplest, so I'll pick that one. X plus y plus z must equal 4. So if x is 1 and y is 1, 1 plus z must equal 4. And of course, z equals 2. So there's my solution for z. And again, the author would probably put the answer in ordered triplet form: x value, then y value, then z value. So the ordered triplet 1, 1, 2 solves the system. One more, we'll call it a day. This one's a little tougher, so Let me get a new layer. Solve. 4x minus 3y plus 5z equals 23. 2x minus 5y minus 3z equals 13. And minus 4x minus 6y plus 7z equals 7. Alright, again I'm going to label these equations 1, 2, and 3 and say we need to solve this system. Alright, equation 1 plus equation 3. If I add equation 1 to equation 3, I see the x variables will cancel out. And I might be able to use that. The resulting sum would be then minus 9y, 5z and 7z is going to be plus 12z equals 23 plus 7 is 30. So I've successfully eliminated the x variable in that equation. And then I'm going to add to that, well, let's see, how can I eliminate x from a different pair? I notice if I multiply the second equation through by 2, I can then add that to equation 3 to eliminate the x variable, much like I did adding equation 1 to equation 3. So let me write that down. 2 times equation 2 plus equation 3. Well, that will give me 2 times 2x is 4x, and 4x minus 4x is 0. The x's cancel out. Minus 5y times 2 is minus 10y. Minus 6y gives me a minus 16y. 2 times minus 3z is minus 6z. And minus 6z plus 7z is 1z. And 2 times 13 is 26, and 26 plus 7 is 33. Okay, so taking equation 2, multiplying it by 2, and adding it to equation 3 eliminates the x variable from that pair and gives me this resulting equation without x. So I've got two different equations with x eliminated. Let me write down the resulting 2 by 2 here. Minus 9y plus 12z equals 30. And minus 16y plus z equals 33. Alright. Now I'm going to solve the resulting 2 by 2. Well, I think I'm going to leave the top equation alone and multiply the bottom equation by negative 12. Because if I multiply the bottom equation by negative 12, I will be able to easily eliminate the z variables. Okay? So the top equation I'll leave alone. The bottom equation, I'm going to multiply by minus 12. Now you need a calculator here. Multiply all terms, both sides, by negative 12. Negative 12 times minus 16y is plus 192y. So this one's a little tougher. These numbers are a little more cumbersome. Now negative 12 times z is going to be negative 12z, and that's just what I want. And negative 12 on the right times 33 gives me a minus 396. Alright, so multiplying the bottom equation through by minus 12 gives me this result. I can now add these equations to eliminate z and then hopefully solve for y. Minus 9y plus 192y is 183y. Don't panic. The z's cancel out, and 30 minus 396 gives me a minus 366. I'm going to divide both sides by 183, of course, and it turns out 366 is a multiple of 183. Of course, now y equals negative 2. So I circle that. Alright, I can go to either of these equations and plug in y equals minus 2 to solve for z. I'll pick the second one. Minus 16 times minus 2 is 32, plus z equals 33, and of course we get z equals 1. Now I'll go to any, alright, I've got two of these variables solved for. Alright, I'll go to any of the original equations in my original system statement, and I think I'm going to use the second one. I suppose no real advantage to one over the other. Let me rewrite it down here. 2x minus 5y minus 3z equals 13. And again, the goal here is to solve for x. When y is minus 2, be careful of signs here. Minus 3 times 1 equals 13. So I get 2x plus 10 minus 3 equals 13. Of course, 2x plus 7 then equals 13. 2x, of course, equals 6. And x is, of course, 3. So I have successfully solved for all three variables. X is 3, y is minus 2, z is 1. X is 3, y is minus 2, z is 1. This is my simultaneous solution to the 3x3 system given. Alright, so a little nastier than the 2x2s, but if you practice these and show good housekeeping, it shouldn't be that much of a problem. Alright, so this will conclude section 3.3, solving 3x3 systems.